So now we will talk about estimation of random variables. So let y be a random variable, and sometime we may be in situation where we need to choose a single value that can estimate or approximate y. So what can be an example scenario? Think about that you are designing a classroom and then you ask yourself, how many students should I consider when I design this classroom? Now, exactly the number of students that are going to sit in this class is random. Sometimes there will be more students, sometimes there will be less students. So in those cases, when you are thinking about how many students I should make this room, we say normally that get an estimate of students. Right? In layman terms, we say get an estimate. What does it mean that you have to guess how many students would be there on the average? And of course, when you actually make the room, sometimes there may be more students, sometimes there will be less students. You may end up in situation when the class is half empty, or you may also end up in situation where there are no place for a student to sit. But you cannot design for every possible case, but what you can do is you can design in a sense that your guess works most of the time. Or let's say your guess works 90% of the time. So in these cases, when we estimate something, we have to also talk about how much uh, good this estimate is. That's where this goodness of estimation is coming from. And then for that, you have to define an error metric, right? To say that something is good or not, you have to characterize this, you have to quantify it by a error. So whenever your estimate is not good, there will be some error. And depending on how large the error is, your estimation would be good or bad. So this is what whole estimation is, that there is some random variable, there is some random experiment and its outcome is that is a random variable, and we have to guess its value before the random experiment happens. Okay, or if this random experiment is going to happen multiple times, uh, then we want to design our system so that it works no matter what the random variable is, or it works for most of the times, depending on the value of random variable. So formally, let's denote, suppose let's denote y hat as the estimate of phi omega, and omega is a deterministic value, is a single guess. So let's say this y hat is nothing but a, some number. So for any outcome, if you do the experiment and you get y omega, the error we define as a minus y omega absolute value. Okay, so if your guess is exactly correct, your error is zero. Otherwise, whether it's less or more, your error will be according to that absolute value. And here you also notice that because y is a random variable, e is actually a function of y. So it's also a random variable. It means depending on what is the outcome of random variable, you get a different value of error. So when this is a random variable, you can talk about different characterization of it, right? What is the distribution of this error? What is the mean or variance of this error? So one metric will be mean. Mean error would be defined as expectation of E, which is nothing but expectation of A minus 1. Okay, and the random variable is Y, so we can integrate it with the distribution of Y, or we can calculate the distribution of E and integrate with that. And we say a good estimator is one where the error is very small. So how do we get a good estimate, right? Remember that here the only parameter is A. So we have to adjust A so that our error is small. One thing we also notice that this is not the only error which is possible. Error many times depends on your design, your system, and there are multiple ways you can define the error. The previous one which we talked about was absolute error. Here, someone can also define error as A minus y omega square. Here also error is random variable, but this is a square error. And the mean of this error would be the mean of a minus y square or a minus y omega square. This is called the mean square error. Again here, if you want to design a good estimator, this should have a small error. Now, depending on what error you want to focus on, you will get a different estimator. So first you have to decide what is your error, and that error depends on many things. Like for example, you are designing a class, and if the student number is less than the capacity, then that's fine. That is not an error for you. Your error will only occur when there is students more than the capacity. Then the student have to stand up, and that doesn't look good. So in that case, you can say that the error is only if y your estimate is less than the value of phi omega. Okay. And depending on how large the error is, your error will increase. Sometimes you also say that having 2 or 3 more students is not a problem. So your error would be something like y omega minus y hat minus 2. Only when this is positive, otherwise the error is 0. So this error will depend on your design, your system, what is your tolerance, and all those things. But for that you have to think about what system you are considering. But once you decide your error, then you can talk about that. Now, if I make a guess, my goal is to make a guess such that the error is minimized. This is what we are going to focus on. So we will take this error, and then we will compute an estimate which will minimize this error. So how can we do this? So our goal is, so this is the function of a, and I want to find a value of a such that this thing is minimized. By notation, we call it arg minimum, which means argument of the minimization of this. So for whatever value of a, this thing is minimized, that is our answer. So we know that to minimize this function, the condition is that its derivative with respect to a should be 0. Right? If that is true, then you can see that this function will have a minima or maxima depending on that, depending on the behavior, and there you can have estimate. So if I differentiate, I have to differentiate this with respect to a. So let me write first the expression of e y minus a square. It is equal to integration of y minus a square with PDF of phi into dy. Now once I differentiated it with respect to a, the limits are independent of a. It's a linear operation. So limit integration differentiation can come inside, and this is the only term which is function of a. So when I differentiate this term, I get 2y minus a, and the rest term is same. And now we will put this equal to 0. So when I put 2y minus a PDF into dy equal to 0, what I get is I can break this into 2 parts. Integration of y minus integration of a equal to 0, and I have cancelled 2. This actually tells us that the integration of y fi dy should be equal to integration of a fi dy. Now this is nothing but the expectation of a, and here if I take a out, this is integration of fi y, which should be 1. So that is just a. So this means that the a is equal to expected value of y. So best estimator of y, which minimizes this mean square error, is the mean of y. Okay, and then you can I'm not proving this, but you can prove yourself that this is a minimizer, not the maximizer, right? So the equal to 0 can happen in both minima or maxima, but you can prove from second derivative there is a minimizer. There are other ways to prove this also without doing the differentiation. So the best estimator of y is actually the mean of y. So if you have no idea of what y is going to be, and your goal is, and you just know the distribution, and your goal is to minimize the mean square error, then in that case, your guess should be its mean value. Okay, and that is most cases we do, right? If you are asked to guess a random variable, you just say, I will guess by its average value. And the error in this case, when I take this estimator, would be E of y minus a square, right? And a is expectation of y. So this is expectation of y minus expectation of y square, which is nothing but the variance of y. So it means that even if you take the best estimator, your error, minimum error, is going to be the variance of it. And you cannot do better than this. So let us talk about estimation when some information is given to us. So given that information and assuming that the information is somehow related to the random variable we are interested in, can that information help us in estimating the random variable better? So we saw in the last example that if we don't have any information, the estimation of y is best guessed by its mean value, and the error is the variance of y. So it means this you cannot do better than that. If you do choose any other random variable, you would get something which is more than variance. You get error which is more than variance. So now we are interested in that if we know somehow some information about y, can we reduce this error? So to formalize this, we will say that let's assume there are two random variables x and y, and they are in the same probability space, and their joint distribution is low. So we don't exactly know, if I know x, I do not exactly know what will be the y, but there is some distribution on y given x. Okay, and let's assume they are not independent. So if they are independent, then it means that if you know x, that is not going to tell anything about y because distribution remains unchanged. But when they are dependent, it means knowing x will tell you something more about the distribution of y. So there is some information in x which tells you about y. So this information, x denote the information about y, right? We know the value of x. And given the value of x, can we tell the value of y? Okay, so that is the main problem. So let us see. So let's assume this estimate is a function of x. Okay, so I am assuming that x is known, and based on that data, I have to estimate y. So this y hat is definitely a function of x. Now our goal is to find what function it should be. And y hat again is a random variable because it's a function of x. So if x changes, this will also change. So error in this case is y minus y hat or y minus fx, which is also a random variable. So now let us first restrict, because f is a general function, finding it may be a little bit difficult. So what we do, we first restrict f to be a linear function. And what can be region? Because you have, when you implement this estimator, it may be easier to have a low complexity estimator. And linear estimation is low complexity. So people say that just give an x, find a linear function which can estimate. Okay, so this will be, of course, not the best estimator given y, because we are restricting on the form of f, but it may be easier. So we'll start with this. So linear means the y hat will take a form of ax plus b. So there are only two parameters, a and b. Okay, that you have to find. And once we know a and b, suppose it is 2 and 3, then your estimator will be 2x plus 3. So that will be your final answer. So how to find this a and b? So error is, let me say again, error is y minus y hat. So y hat is ax plus b. So error is y minus ax plus b. And I'm interested in the square error. So square error will be y minus ax minus b whole square. And the average of that would be y minus ax minus b whole square as expectation of that. And our goal is to find a and b such that this error is minimized. So we want to find the argument of this minimization function. So the way we would do is we will differentiate. There's a two variable function. So we will a and b. So we will differentiate with a and b and put it equal to 0. And we will get two conditions, and solving them together, we should be able to get a value of a and b for which this is minimum. So let us take the first one. Let me first write the expression of this expectation y minus ax minus b, because there are two random variables involved. This expectation would be integration of y minus ax minus b whole square of x, y, x, comma, y, dx, dy. Okay, remember that this x is also random and y is also random. And I want to find a linear estimator which has an error, average, minimum error averaged over all possible values of outcomes. So in that case, I want to minimize this, the joint distribution. Sorry, the joint expectation. So I will first differentiate with respect to a, and again this is a linear integration. So differentiation with respect to a will come inside, and this is the only function which is this is the only term which depends on a. So I differentiate this and I get 2y minus ax minus b into x, and then we have this remaining term, and we want to make it equal to 0. Now if you notice this is nothing but 2 times expectation of y minus ax minus b into x. And I want to be equal to 0, so I will cancel 2. So the expression I would get is expectation of y minus ax minus b into x should be equal to 0. And expectation is linear, so I can break this into the following format. It should be, it can be written as expectation of xy minus a into expectation of x square minus expectation of bx, or b of expectation of x should be 0. This is our first condition, and here we because we know the joint distribution, we can calculate exy and e of x square and e of x. One thing before proceeding, I will tell you about this condition. This condition says that y minus ax minus b and x should be orthogonal. Recall the definition of orthogonality if two random variables are orthogonal if e of yx is 0. So in this case, this is one random variable, this is another random variable. And because their expectation of their product is 0, this means one condition is nothing but a statement that x and y minus ax minus b is orthogonal. Okay, and ax minus b is y hat, so this means y minus y hat and x is orthogonal. And this is error. So other way to say is error and x. Error and given information should be orthogonal to each other. So we will come back to this once more, but for now just remember the another interpretation of this condition. Now we will differentiate with respect to b. So once we differentiate, again this is the only term which depends on b, so the differentiation will come inside. And when I differentiate this, I get 2y minus ax minus b. And this is another, this should be equal to 0. This means this is another way to say this, expectation of y minus ax minus b is 0. If you break it, it means ey minus aex should be equal to b. If I put two equations together, they say e of xy minus a of ex square minus bex equal to 0, ey minus aex equal to b. Now notice that although we know the whole distribution, only parameters we actually needed to know to solve this was e of xy, e of x square, e of x, and e of y. So if I know these four values, the mean of x, mean of y, mean of x square, and mean of xy, we don't need the rest distribution. Now from the second equation, The value of b is ey minus aex. If I put this value in the first equation, what I get is exy minus aex square minus, in place of b, I put ey minus aex into ex equal to 0. Now I multiply them together to get exy minus ey into ex minus aex square plus aex square is equal to 0. Now our goal is to find value of a. So value of a will be equal to exy minus ex divided by ex square minus ex square. Now if you notice, this is, we call it covariance of xy. So covariance of xy is expectation of xy minus product of mean of x and y. And this below term is called the variance of x, which is the second moment minus the square of the first moment. So a is given by cxy minus sigma s square and b is given by ey minus aex, and I put the value of a to get the value of b. So the final expression I get is a is equal to cxy upon sigma x square and b is equal to my mean of y minus cxy upon sigma square into mean of x. So the best estimator of x given y is ax plus b. A is cxy upon sigma square x and b is my minus cxy sigma square mx. Now you can compute the expectation. Again, this is a random variable because it depends on x. So you can calculate the mean and you can also compute the error y minus e square, sorry, y minus y hat square, and then compute the average error. Now we take the special case. In the first, we assume x and y are independent, sorry, dependent. Otherwise, there will be no mutual information. Let us see what will happen when x and y are independent actually. So if they're independent, then this exy is just ex into ey. So this should be 0. So cxy is 0 if x and y are independent. This is the expression. If you put this and this 0, what you get is y hat is just mean of y. Which is the previous example where we say that if you don't have any information, the best guess would be, best estimator will be just the mean of their random variable. Here we find out that even if we know x, the best estimator is still the mean of y because x does not have any information about x. It's just independent of y. It doesn't change. Knowing x does not change the distribution of y. So there is no role of it in the estimation. Let us come back to this orthogonality condition once more, where we say that the error should be orthogonal to the information. Right? So it means that when you have to find the estimator, you find such a way that the remaining error becomes orthogonal to the x. Okay, so this may look like a projection to you that you want to find a y hat such that the remaining error is orthogonal to x, and because you only know x, you don't have any other information, this error cannot be further reduced because it has no component of x in it. It is that all the component in the error is now orthogonal to x. In the past, we have find out the best linear estimator giving information x. Now in that case, we said that y is equal to a function, y hat is equal to function of x, but we restricted f to be just the linear function of x. Now we will remove that restriction, and now y hat can be any function of x. So we have to find now this function g, which will give me the lowest error. So the proof is a little bit involved and is different than it's not as simple as the one we have seen in the past. So let us see how we can do that. So what we want to do is minimize this error y minus y hat square, and y hat is gx. So our goal is to find a g such that y minus gx square expectation is minimum over every possible function of x. What we do here is I'm going to add and subtract conditional expectation of y given x. Once I do that, it will be this term plus this term square. Now I will expand this by using the formula of the square of the sum of two numbers, a square plus b square. That will be a square plus b square plus 2ab. So it will be expectation of y minus conditional expectation square plus eyx minus gx square, and then the plus 2 and product of these two. And these are all plus, and expectation is outside, so I can always break this because of the linearity of expectation. So what I get is expectation of y minus ey given x square plus expectation of expectation yx minus gx square plus expect 2 into expectation of y minus expectation of yx, and then multiplied by expectation of yx minus gx. Now let us focus on this term, the third last term. This term is nothing but expectation of y minus ey given x and ey given x minus gx. So let me multiply this, expand this term by expanding the second term to get expectation of eyx into y minus eyx minus gx, e of gx into y minus ey given x. Now I want to show that this term is actually, both terms are 0. Let us start with this one. So regardless of what is the value of g, this term should be 0. How can I prove this? So this is just this I can break to get expectation of y into gx minus expectation of y given x into gx. So expectation of y g given x, using the conditional chain law, total probability law, I can break this expectation, which is with respect to x, y, into two parts. One is expectation given x, and then I will decondition with respect to x. So this is expectation with respect to x, and then inside there will be expectation y given x of y gx. Now notice that in this inner integration expectation, it is y given x, so I have to this is conditional on x. So gx is a function of x. When I condition on x, gx is known to me. So this gx will come out side of the inner expectation, and what I get is e of y given x into gx. Okay, this we have covered. This result we have covered when we were talking about this conditional expectation. That if you try to compute the conditional expectation of y given x of some function of x, then the result will be just that function of x. Now this is same as the second term, because the both terms are same, the minus of the term would give me 0. So the second term, this term, whole term is 0. Now if you look at the first one, in this is very similar to this term. Only difference is instead of gx there is ey given x. But note that first result we have proved for any g. And in this case, ey given x is nothing but a function of x. So this should also be 0. So once you have proved that the last term is 0, only thing you are remaining in this error is expectation of y minus ey given x square plus expectation of eyx minus gx square. Now tell me, our goal was to find gx which will minimize this. No matter what g will you take, the first term remains unchanged because there is no g here. There is only g here. Now tell me what g you can take such that this term is minimized. Note that this is expectation of sum square. So if this is nothing but the integration of this term with respect to some period. Because this is positive term, the integration will always remain positive. So this term is always positive. And what is the minimum value a positive can take? If possible, 0. If you can find something is 0, then that is the minimum value of that positive number, which is possible. If you take any g, no matter what g, it cannot be negative. So the minimum value, the best value you can hope for is 0. And is there a value g for which this will become 0? Yes. If I take gs as ey given x, that is also a function of x. So then this term will be 0. And no other g can make this 0, right? So g of x is ey given x. This is the function we found, that if you take this function, then you will get the minimum error. So the best estimator of y given x is conditional expectation of y given x. Okay, so when we computed this in the original place, we thought it was just an integration condition with conditional distribution of y, right? But this is more than that. Conditional expectation is actually the best estimator of y given x, right? So if you know some information x and you want to get a guess of y, just compute the conditional expectation of y with respect to the given information. And not just this, we also prove one more result. We want to show that if you take any function, right, f of x, this estimator also satisfies one more condition, that the the expectation of y minus y hat into fx is 0. Recall y minus y hat is error and fx is any function of the information. So this means that this conditional expectation, the best estimator, actually have this property that the remaining error is orthogonal to any function of the information, right? It means no matter what function of whatever function you take, right, whatever way you modify the information, adding that to the estimate is not going to help in the error. The error will still remain same. Okay, how do I prove this? Is almost the same way. Start with EYFX, and then I will break this into conditional expectation with respect to x, and then deconditioning with respect to x. So now this term fx is independent. It's a function of x. So given x, it will come out of the expectation. So what I get is expectation of expectation y given x into fx, which is the second term. So the minus would be 0. So this tells me the error y minus y hat is orthogonal to fx if you choose this particular estimator. And if you choose any other estimator, then this may not be the case. And that is why that is not the best estimator, because there is some error still left, which can be which is a function of, which is not orthogonal of the information, which can be added back to the estimator.